Bismillahirrahmanirrahim. The thought of the day is La yukallifullahu nafsan illa wus'aha. Allah does not burden a soul beyond that it can bear. Assalamu alaikum. My name is Dr. Inshrah Khan and I am a PGR of Community Medicine and Public Health at King Edward Medical University, Lahore. Today the topic of my presentation is Introduction to Probability, Addition Rule, Multiplication Rule, and I'll be presenting this topic under kind supervision of Professor Dr. Saira Aksar. Our learning outlines will be basics of probability, rules, types and interpretations, applications, recent updates, and then MCQs. At the end of this presentation, the participants will be able to define probability, calculate the likelihood of events, and apply fundamental probability rules, differentiate between classical, empirical, and subjective probability, and interpret applications. Probability and basics. Probability is simply how likely something is to happen. Whenever we are unsure about the outcome of an event, we can talk about the probabilities of certain outcomes, that how likely they are to occur. The idea of probability is based on observations. Probability describes what happens over many trials. An event is the result of an observation or experiment or the description of an outcome. If E is an event, then the probability of this event E is equal to number of favorable outcomes divided by the total number of possible outcomes. We'll explain this by examples. First of all, flipping of a coin. If we toss a fair coin, there are two possible outcomes, a head H or a tail T. That means total number of outcomes are 2. So probability of having a head equals PH is equal to 1 by 2. Because there are only two outcomes, head and tail, and there are 50% chances of both outcomes. So total number of outcomes will be 2 and 50% of 2 is 1. And also heads in on one side of a coin. So probability of heads would be 1 by 2. Another example, choosing a pillow. There are 6 pillows in a bed. 3 are red, 2 are yellow, and 1 is blue. What is the probability of choosing a yellow pillow? The probability is equal to the number of yellow pillows in the bed, that are 2, divided by the total number of pillows, that are 6. So 2 by 6 or simply 1 by 3. Another example, there is a container full of colored bottles, red, blue, green, and orange. Some of the bottles are picked out and displaced. Hassan did this 1,000 times and got the following results. Number of blue bottles picked out were 300, red 200, green 450, and then orange 50. What is the probability that Hassan will pick a green bottle? Because there were 1,000 bottles that were picked out, and out of this green were 450. So probability of green would be 450 divided by 1,000 or simply 0.45. Probability experiment. A probability experiment is a chance process that leads to well-defined results called outcomes. An outcome is the result of a single trial of a probability experiment. The different examples of probability experiments are flipping of coin, rolling of dice, drawing a card from a deck, picking out bottles and pillows, as I have mentioned earlier. Moving forward to sample space. A sample space is a set of all possible outcomes of a probability experiment. Here are some different examples. Here is the experiment and here we have sample space. Whenever we toss one coin, there are two possible outcomes. Either the coin will land on head or on tail. Whenever we roll a dice, it can show 1, 2, 3, 4, 5, and 6. So it will be its sample space. If we have to answer the question in true or false, there are two possibilities. Either it will be true or it will be false. Whenever we toss two coins, there is possibility that we have head, head, tail, tail, head, tail, or tail, head. So all of these are the sample spaces of these experiments. Representation of sample space. Sample space can be represented either in the form of list, table, or T-diagram. We'll take the example of tossing of two coins. When two coins are tossed, represent the sample space for this experiment by making a list, a table, T-diagram. This is the list and these are the possible outcomes, the 4 possible outcomes that I have already told you. This is the table form and this is T-diagram. What is T-diagram or probability tree? The T-diagram helps to organize and visualize the different possible outcomes. Branches and ends of the tree are the two main positions. Probability of each branch is written on the branch, whereas the ends are containing the outcome. This is the probability tree. This is the starting point. We have the branch here, and this is the probability of this branch. These are the ends where we have written the outcomes. This is another example of tossing of 2 coins. First coin, its outcome can be heads or tail, and then second coin, its outcome can be either head. So this will be the outcome if it lands on tail. These will be the outcomes, and similarly, these are the outcomes if the first coin showed head and then second coin showed either head or tails. In order to make our concept a little bit clear, we'll consider this example of tossing of 2 coins and answer the following questions. What is the probability of flipping 2 heads, at least 1 head, no heads, 1 head and 1 tail, not more than 1 tail? We can tabulate the answers as follows. Whenever we toss 2 coins, there are 4 possible outcomes. Remember, 4 possible outcomes: head, 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 tail, head, or tail, tail. So now we have to consider the probability of having 2 heads, because this is possible only in this event. So we have probability of having 2 heads is equal to 1 by 4. If we have to find the probability of having at least 1 head, this is possible in 3 out of the 4 events. So probability would be 3 by 4. Similarly, no heads in only 1 event, so 1 by 4. 1 head and 1 tail is possible in 2 events. These are the 2 events, because the other 2 events would be head, head, or tail, tail. So we'll have probability of 2 by 4, and similarly, no more than 1 tail, probability would be 3 by 4. Event. An event consists of set of outcomes of probability experiment. Event can be simple, which has only single outcome, or compound when we have 2 or more outcomes. We'll now consider different types of events. First of all, mutually exclusive events. These are the events that cannot occur at the same time. They have no outcomes in common. That is, if one event happens, the other event cannot happen. Example, in the 1 coin example, E1 heads and E2 tails. Event 1 heads and event 2 tails are mutually exclusive. Because whenever we toss a coin, it will either land on heads or on tails. It is not possible for one coin that was tossed a single time to land on heads and tail at the same time. So mutually exclusive events, here you can see this is an event A and this is an event B. These are completely different events. Similarly, if we have a race or something, anything where we say that 42% are cats and 38% are dogs, so these are two different experiments that are not related to each other in any way. Such events are mutually exclusive events that cannot happen together or at the same time. Moving forward to the non-mutually exclusive events, these are the events that can happen at the same time. Examples include driving and listening to the radio, even numbers and prime numbers on a dice, losing a game and scoring, or running and sweating. These events can occur simultaneously. Non-mutually exclusive events, here you can see that this is an event A, this is an event B, and this is the shared space of both event A and B, where both of these events occur together. Similarly, we can say that these are the people who like cats. This circle represents people who like dogs, and this shared space includes individuals who like both cats and dogs. So mutually exclusive events cannot happen together, and non-mutually exclusive events can happen together. This is a Venn diagram. Wait a second. Sorry. This is a Venn diagram. We can see that these are non-mutually exclusive events with shared space, and this is mutually exclusive events with no shared space. Moving forward to independent events. Events are said to be independent if the outcome of one event does not affect the outcome of the other. If the two events are not related, they are said to be independent events. Example, outcomes of rolling a dice 2 times or 2 die at the same time are independent events. Rolling a dice and tossing a coin are independent events. Dependent events. Events are said to be dependent if the outcome of one event affects the outcome of the other. In probability, dependent events are real life events and rely on another event to occur. Example, Samina scored well in test because she studied for it. Not paying your power bill on time will result in cutting off power supply. The gym class had a cricket match because Fussy got a bat and a ball. Similarly, we'll consider this example of 5 balls in a bag. 2 are blue and 3 are red. If we take out a red ball, then we have the probability of having 2 balls, 2 in 4. And if we take out one blue ball, then the probability would be 1 by 4. So this is an dependent event, because the probability of having blue balls depends upon this event, that either we take out red ball or blue ball. Difference between mutually exclusive events and independent events. If two events A and B are mutually exclusive, then they cannot happen together. Two events A and B are said to be independent. They can happen together but are never related to each other. We'll consider this example. Outcomes of rolling a die are mutually exclusive events. You can either get 5 or 6, but you can never get 5 and 6 at the same time on the same die. So this is an example of mutually exclusive events. Contrary to this, outcome of rolling a dice 2 times or 2 dice at the same time. This is an example of independent events. Going forward to the rules of probability. Probability rule number 1, it states that the probability of any event E is the number, either fraction or decimal, between and including 0 and 1. This is denoted by probability of event E is less than or equal to 1 or greater than or equal to 0. This rule states that the probability cannot be negative or greater than 1. Rule number 2 states that if an event E cannot occur, its probability is 0. Third rule states that if an event E is certain and it is bound to happen, then its probability would be 1. Similarly, rule number 4, it states that the sum of probabilities of all the outcomes in the sample space is 1. Sum of all outcomes in a sample space is 1 and always 1. Whenever we have more than one event, the probability of 2 or more events can be determined by addition rule and multiplication rule. If OR is used, this is represented by this symbol and we apply the addition rule. If AND is used, this is represented by this symbol and we apply multiplication rule. Remember, OR stands for addition rule and AND stands for multiplication rule. Addition rule states that the probability of 2 events is the sum of the probabilities of 2 events that will happen. For mutually exclusive events, we will simply apply the simple addition rule, and for non-mutually exclusive events, we'll have overlap adjustment rule. For mutually exclusive events, addition rule number 1 applies, that states that 2 events A and B are mutually exclusive. The probability that A or B will occur is simple sum of both probabilities, probability of A and B. Consider this example. A single 6-sided die is rolled. What is the probability of rolling 2 or 5? Probability of having 2 would be 1 by 6. Similarly, probability of 5 would be 1 by 6 because there are 6 sides of a standard 6-sided die and 2 is written only on one side. Similarly, 5 is written only on one side. So probability would be 1 by 6 for both of these things. So probability of 2 or 5 is equal to simple sum of both probabilities. And after doing simple math calculations, we have the answer of 1 by 3. This is the formula that applies here. For non-mutually exclusive events, we have addition rule number 2 that states that when events are non-mutually exclusive, then probability of A or B is equal to probability of A plus probability of B minus probability of the shared space of A and B. We do this to prevent duplication. You can see that these are mutually exclusive events. So we apply this formula of simple sum of both probabilities, and this is non-mutually exclusive event with a shared space. So we apply the formula of probability of A plus probability of B minus probability of this shared space of A and B. Consider this example. In a hospital unit, there are total 8 nurses and 5 physicians. 7 nurses and 3 physicians are female. This means that 1 nurse and 2 physicians would be males. If a staff subject is selected, find the probability that a subject is a nurse or a male. Consider the formula that I have discussed earlier. We have to find the probability of A, that would be probability of nurses, probability of B, that would be probability of males, and then probability of the shared space. You can see that what are the total number of nurses? 8. Total number of nurses are 8. You can see here too. And total number of subjects are 13. So probability of nurses would be 8 by 13. Probability of males would be total males are 3. So male, it would be 3 by 13, and probability of nurse and male, the shared space, all those nurses that are male, and we have only one male nurse. So probability of nurse and male, the shared space would be 1 by 13. You can see here probability of nurse 8 by 13, male 3 by 13, male and nurse 1 by 13. When we apply this formula of probability of A plus probability of B minus probability of shared space, we get the answer of 10 by 30. You can do the simple maths here. Another example, in a math class of 30 students, 17 are boys and 13 are girls. On a unit test, 4 boys and 5 girls made an A grade. If a student is chosen at random from the class, what is the probability of choosing a girl or an A grade student? Probability of girls would be, what is the total number of girls? 13. And total number of students were 30. So probability of girl would be 13 by 30. Probability of A grade students would be 5 plus 4, 9, 9 by 30. And probability of girl and A grade, the shared space. There are only 5 girls who scored A. So probability of girl and A grade would be 5 by 30. After doing this simple maths and application in this formula, we get the result of 17 by 30. I'll do this maths for you. This 13 by 30 plus 9 by 30 minus 5 by 30, because 30 in the denominator is common. We'll simply add 13 and 9 and subtract 5. We get the simple answer of 17. So 17 by 30 would be the answer. Moving forward to the multiplication rule. The multiplication rule states the probability of two events is equal to the product of the probability of both events. For independent events, we have multiplication rule number 1 that states that probability of both events occurring is simple product of both probabilities. Probability of A multiplied by probability of B. Consider this example. A coin is flipped and a dice is rolled. These are two independent events. Find the probability of getting a head on a coin and a 4 on a dice. Probability of head would be 1 by 2 because there are two sides of a coin and head is only on one side. Probability of having 4 on a dice would be 1 by 6 because there are 6 sides of a dice and rolling a dice can result in 6 possible outcomes. So these will be the probabilities, and by multiplying both these probabilities, we get the simple answer of 1 by 12. 1 by 2 multiplied by 1 by 6. So 1 by 12 would be answer. For dependent events, when two events are dependent, the probability of both occurring is probability of A multiplied by conditioned probability of B on A. Remember, conditioned probability of B on A. So there would be some condition, some dependency in such examples. We'll clear this concept by this example. Mind that a jar contains 20 red balls and 10 blue balls. Two balls are drawn from the jar, one after the other, without replacement. What is the probability that the first ball and the second ball both are red? This and represents that we'll apply the multiplication rule. Let's A and B denote the two events regarding the first and second ball drawn being red. We must find this or this or this. All of these three represent that we are finding the probability of A and B and we are multiplying, or we are applying the multiplication rule. So probability of A, that is probability of red ball in first draw. What would be this probability? 20 by 30. Why? Because there are 20 red balls in this jar and total balls are 30. 20 red and 10 blue. So 20 by 30 would be the probability. Remember that one red ball has been drawn and it is not replaced. Now we have 19 red balls and 10 blue balls in the jar. The probability of drawing a red ball again in the second draw is an example of conditional probability where the drawing of the second ball depends on the drawing of the first ball. Hence, conditional probability of B on A will be 19 by 29. Why 19? Because there are 9 red balls and 10 blue balls. And we have to pick out red ball again. So 19 divided by 19 plus 10, 29. After application into this simple formula, we get the answer of 38 by 87. 20 by 30 multiplied by 19 by 29. So answer would be 38 by 87. We'll consider another example. Sadia has a bag of candies. In bag, there are 5 red candies, 8 green candies, and 3 orange candies. She takes out one candy, records its color, and puts it back in the bag. She then takes out another candy and repeats the same process. What is the probability of taking out a green candy and then a red candy? So probability of A would be the probability of these green candies. What are the total number of green candies here? 8. There are 8 green candies. So 8 divided by 16. Why 16? Because the total number of candies 5 plus 8 plus 3 equals 16. So 8 by 16 would be probability of A. And then condition probability of B on A. Because the candies have been replaced, that is, they have been put back in the bag. So there is no deficit of the candies, contrary to the last example where there was no replacement. So we have to calculate the probability of B, that is probability of these red candies. And what are the total number of red candies? 5. So 5 divided by 16, again 16, because replacement has been done. So after multiplication, we get the answer of 5 by 32. Complementary events. The complement of an event E. Remember that there had been a probability experiment and it had an outcome. That outcome was the event E. Now we are talking about the complement of this event E. This is the set of outcomes in the sample space that are not included in the outcome of event E. The complement of E is denoted by E bar. Read E bar. When a dice is rolled, for instance, the sample space consists of all possible outcomes, that is 1, 2, 3, 4, 5, and 6. The event E of getting odd number consists of 1, 3, and 5. The event of not getting an odd number or event of getting even numbers or its complement or its opposite, you can say whatever you like, is denoted by E bar and consists of 2, 4, and 6. For complementary events, we have a probability of this E bar is equal to 1 minus probability of E, or probability of E. If we take this probability of E here and probability of E bar here, we get this formula, probability of E is equal to 1 minus probability of E bar, or simply probability of E plus probability of E bar is equal to 1. This follows the probability rule number 4 that stated that the sum of probabilities of all possible outcomes in a sample space is always equal to 1. This formula is used to calculate the probability of the event or the complement if one or the other is known. We do this by subtracting from the 1. If we have the probability of an event, we subtract this probability from 1 to get the probability of the complement, or if we have the probability of the complement, then we subtract this probability of complement from 1 to get the probability of the event itself. This is the pictorial representation of whatever I told in the complementary events. We'll come back to this slide if we are left with some time. Moving forward to the types and interpretations of probability. There are three basic interpretations of probability: classical, empirical, or subjective. What is classical probability? It assumes that all outcomes in a sample space are equally likely to occur. When a single dice is rolled, each outcome has the same probability of occurring. Since there are 6 outcomes whenever we roll a die, each outcome has the probability of 1 by 6. This is the formula for calculating classical probability, that is number of outcomes in event E divided by total number of outcomes in the sample space, number of events in E divided by total number of outcomes in the sample space S. Probabilities can be expressed as fractions or decimals or where appropriate percentages. If you ask what is the probability of getting a head when a coin is tossed, typical responses can be one of the following three: 1/2, 0.5, or 50%. What is empirical probability? It is relies on actual experience to determine the likelihood of outcomes. In empirical probability, we might roll a given dice 6,000 times, observe the various frequencies, and use these frequencies to determine the probability of an outcome. The formula for empirical probability or relative frequency probability is frequency for the class, denoted by F, divided by total frequencies in the distribution, denoted by N. Consider this example. Suppose, for example, that a researcher for the American Automobile Association asked 50 people who plan to travel over the Thanksgiving holidays how they will get to their destination. The results can be categorized in a frequency distribution as follows. 41 individuals said that they would be driving, 6 said that they would fly, and 3 said that they would travel by train or bus. Now, probabilities can be computed for various categories. For example, the probability of selecting a person who is driving is 41 by 50, since 41 out of 50 people said that they were driving. Subjective probability, it uses probability value based on educated guess or estimate, employing opinions and inexact information. In subjective probability, a person or a group makes an educated guess at the chance that an event will occur. This guess is based on the person's experience and evaluation of a solution. Example, a sports writer may say that there is 70% probability that the Pirates will win the pennant next year. A physician might say, based on her diagnosis, there is 30% chance that the patient will need an operation. Prior probability is based on prior knowledge, experience, or results derived from prior data collection activity. Posterior probability obtained by using information or updating or revising prior probability. Applications of probability. These are simple applications in our daily life that include choosing a card from a deck of cards, flipping of coin, throwing a dice in the air, pulling a red ball out of a bucket of red and white balls, and winning a lucky draw. These are some other examples from professional lives. These include risk assessment and modeling in various industries, weather forecasting or prediction of weather changes, team winning in a sports based on the players and strength of the team, in share market chances of getting hikes of share price. Moving forward to the recent updates, statistics and probability for machine learning. This article was published in Springer in 2024, May 2024. This chapter delves into the critical role of statistics and probability in machine learning, starting with an overview of random experiments and variables. It progresses to cover essential topics such as set theory, probability, conditional probability, and key theorems such as Bayes' theorem and central limit theorem. This discussion extends to distribution functions, the significance of expected values and variance, and the normal distribution, along with a variety of other distributions relevant to machine learning. By exploring these statistical concepts, this chapter aims to equip readers with the necessary knowledge to effectively engage with machine learning models and understand the statistical underpinning of algorithm performance and data analysis. Moving forward to the multiple choice questions. Ali and his younger brother were playing a game using a standard six-faced die. In one round, Ali asked his brother to guess the chances of getting an odd number when the die is rolled once. What should be the probability of getting an odd number in a single throw of a fair die? A, 1 by 2, B, 2, C, 4 by 2, D, 5 by 2, or E, 3?
A.
A.
Yes, the correct answer is A, because in a standard six-sided die, we have six sides and odd numbers are present on three sides. So probability would be 3 by 6, or simpler words, 1 by 2. Sarah is playing an online game where her probability of winning is 0.65. What is the probability that she will lose the game? A, 1.05, B, 0.60, C, 0.35, D, 0.80, or E, 0.90?
C.
Charlie.
It's E.
B.
The correct answer is Charlie, because the probability of winning is 0.65. Remember that probability rule number 4 states that the sum of probabilities of all possible outcomes in a sample space is always equal to 1. So the experiment was winning or losing a game. If the probability of winning is 0.65, the probability of losing must be 0.35 for sum of both of these two events to be equal to 1. So Charlie would be the answer. While playing football, Hamza scored a goal but also got slightly injured during the same play. His friend remarked that these two events outcomes occurred together. What is the nature of these events? A, mutually exclusive events, B, non-mutually exclusive events, C, complementary events, D, certain events, or E, dependent events?
Dependent events. E.
Alpha.
ए नहीं होगा.
Correct answer would be beta, non-mutually exclusive events, because these two events occur together. Hina tossed two fair coins to see if she could get both landing on heads. What is the probability of getting two heads in this experiment? A, 1 by 6, B, 1 by 2, C, 1 by 3, D, 1 by 4, E, 2 by 6.
Beta.
1 by 3.
Beta.
2 by 6. E.
Correct answer would be 1 by 4, because whenever we toss two coins, there are four possible outcomes. Either we get head head, head tail, tail head, or tail tail. And probability of both coins on landing on heads is possible only on one outcome, that is head head. So our answer would be D, delta 1 by 4. Moving forward to the next MCQ. In a class, a student's final grade depends on the number of hours they spend studying. If they study more, they are likely to score better. What kind of event does this situation describe? A, independent events, B, complementary events, C, dependent events, D, mutually exclusive events, or E, impossible events?
C. Dependent events.
C.
Yes, the correct answer is
Dependent.
Charlie. Yes, the correct answer is Charlie, dependent events, because the outcome of an event depends on another. Ahmed is rolling a standard six-sided die. He is asked to roll a 7. What is the probability of this event happening? A, 1, B, 0, C, infinite, D, cannot be calculated, or E, none of the above?
None of it. E.
The correct answer would be B, 0, because probability rule number 2 states that if we know that an event cannot occur, its probability is 0. If we are certain that an event will occur at any cost, its probability would be 1. And a standard six-sided die has six sides, and there are 1, 2, 3, 4, 5, and 6 written over it. We cannot roll a 7. So answer would be 0, because it is not possible to get 7 when we are rolling a standard six-sided die. Moving forward to the next MCQ, these will be calculation based. The next 4 MCQs will be calculation based. So please get ready. Its jar contains 6 orange marbles, 3 purple marbles, and 4 black marbles. If a person randomly selects a marble, what is the probability that it is either an orange marble or a black marble? A 3 by 13, B 6 by 13, C 2 by 13, D 10 by 13, or E 4 by 13. You can apply this formula, this simple addition formula, addition rule number 1. We have to calculate the probability of orange marble and black marbles. There are 6 orange and 4 black marbles.
Delta.
10 by 13.
Yes, the correct answer is 10 by 13
Yeah.
because we have to add this and this. 6 plus 4 equals 13. Sorry, 6 plus 4 equal 10. I'm really sorry. 6 plus 4 equal 10 and 13 were the total number of marbles. So delta would be the answer. In a class, 6 by 20 students study music, 9 by 20 study photography, and 3 by 20 study both music and photography. If a student is randomly selected, what is the probability that they study either music or photography? This will be the formula. The options are 1 by 5, 3 by 5, C is 2 by 5, D is 2 by 7, or E is 6 by 5.
Beta 3 by 5.
Anyone else? Yes, the correct answer would be beta. Why? Because application of this formula, we will get probability of A, that would be 6 by 20, probability of B, that would be 9 by 20, and then subtraction of the probability of the shared space, that would be 3 by 20. 20 would be in the same in the denominator. We'll first add 6 and 9. 6 plus 9 equals 15, and 15 minus 3 equals 12. 12 by 20, both of these are divided by 4, so we'll get the simple answer of 3 by 5. Moving forward to the next MCQ, a spinner with 4 equal sections, red, blue, green, and yellow is spun and a die is rolled. What is the probability of landing on blue on the spinner and rolling a 6 on a die? A 1 by 24, B 1 by 12, C 1 by 16, D 1 by 20, or E 1 by 8. This is the formula.
Alpha.
Any other wild guesses?
It's E.
The correct answer is alpha 1 by 24. Why? Because in a spinner we have 4 equal sections. Probability of having blue on a spinner would be 1 by 4. And on a die we have 6 sides. So probability of getting 6 on a die would be 1 by 6. 1 by 4 multiplied by 1 by 6 equals 1 by 24. Last MCQ, a bag contains 7 red balls and 3 green balls. If a ball is drawn twice, what is the probability of drawing a red ball and then a green ball? Remember that no replacement was done. Option set is A 21 by 90, B 21 by 80, C 21 by 70, D 21 by 60, or E 21 by 50. This is the formula. Probability of A and B equals probability of A into conditioned probability of B on A. It's a little bit tricky. The correct answer would be alpha 21 by 90. Why? Because the bag contains 7 red balls and 3 green balls. First of all, we have to find the probability of having a red ball. Probability of A would be probability of red ball. What are the total number of red balls? 7. So we'll have probability of red is equal to 7 by total number of balls 10. 7 by 10. Here we'll have 7 by 10 and we have to multiply this by condition probability. Remember that I said that no replacement was done and 1 red ball has been taken out. So we now are left with 6 red balls and 3 green balls. And total number of balls are 6 plus 3, 9. So probability of B, that is green ball, total number of green balls are 3. So we will have probability of green equal to 3 by 9 because there are 9 red balls now. Here we had 7 by 10. Here we have 3 by 9. 7 into 3, in the numerator we have 7 here and 3 here. 7 into 3 equals 21. That is, by the way, same in all option set. And in the denominator we had 10 here and 9 here. 10 into 9 equal 90. So A would be the answer, 21 by 90. This is the key to all MCQs. This is the link to our YouTube channel where this presentation will be uploaded. And thank you for your attention.
Thank you, Dr. Sava. It
Thank
was
you.
very difficult task and you has done is very fairly
Thank you
nice.
so much. Thank you so much. It was a wonderful presentation.
Thank you all. Allah Hafiz.